so explain how the results in parts B1 and B2 could be obtained through a judicious choice of a dividing plane through the cylindrical and spherical tanks. So I'm going to start with the sphere first, since that one's a little easier to understand. So in that problem, we were looking at half the sphere, and in that half, there was fluid pushing against the wall of the tank, right? And so we need to remember that the acceleration of that fluid pushing against the tank was 0. So that meant the forces pushing against, or the forces pushing against that fluid from the wall, so the force of the wall also needed to be 0, right? So the acceleration of fluid and the force of the wall would be equal to 0. And the same thing applied to this side. And the fluid, the forces pushing against the wall, and the forces pushing against the fluid were both equal, right? So since these two are equal, we can look at the cross-sectional area of this tank, which was a circle in this case. And we need to remember the equation that P is equal, or pressure is equal to the force times area. In this case, we needed to find all of the horizontal forces pushing against the wall, right? So we're left with the pressure times area. Well, what's that area? That area would be the cross section of the sphere, which is just a circle with a radius of r. And so the force needs to be perpendicular to that cross-sectional area, right? And since we are looking at the horizontal forces only, because we're only looking at horizontal forces, we can say that that horizontal force is perpendicular to that cross-sectional area. So this would be the force. So all we need is the force involved. Well, all we need to know is the area in order to get the force involved. So what's the area of a circle? Pretty self-explanatory, pretty straightforward. That area would be pi r squared. So the formula would be P times pi r squared, and this would give us f of x equal to P times pi r squared, and that was the exact same expression to represent all the horizontal forces acting on the tank wall. Well, we can also take a look at the cylindrical tank. Recall that when we split it in half, it's technically a rectangle. So we can look at the spherical tank as a rectangle, or its cross-section, I should say. And the same concept would apply. So we had that fluid pushing against the spherical tank. Gotta change color. That fluid is pushing against that wall, and that wall would be pushing against the fluid. And so we can have that force as the perpendicular force for this cross-sectional area. And so this cross-sectional area would be height, and since it's a cylinder, we had radius, and so this would technically be 2r, because there are two values of radius. So we use the same equation, P is equal to F over A, multiply both sides by A, and then figure out the cross-sectional area. You're left with P times A, which in this case it would be height times 2r. Let me rewrite this actually. And this would have been the exact same equation we got that represented all the horizontal forces acting on that spherical tank.